All right. Can everyone hear me? All right. So again, I'm Michael Carbin, and today I'm going to talk a bit about approximate computing. And as Steve actually pointed out, Catherine wanted us all to put up a slide that talks about where we came from and what constitutes our life. And I was born in California. I did my bachelor's and CS at Stanford, and my advisor was Monica Lamb. Monica these days does a lot of work in HCI, but she's one of the co-authors on the Dragon book, for the compiler's book. So if you're familiar with that book, then you're familiar with Monica Lamb. She's actually been around in the programming language community for quite a long time. At graduate school, I went to MIT, and my advisor was Martin Reinard. If you have not met him or do not know of him, you most certainly will if you stay in this community, just because he has a very interesting personality, as some would say. And I, of course, took a very leisurely 8 years to get through graduate school there. You can certainly talk to me about how you survive as an nth-year graduate student if you have questions along that line. And then after that, I became a researcher for a year, doing pre-sabbatical, as people call it, where I took a year off between graduate school and starting my professorship, where I was a researcher at Microsoft Research. And frankly, a lot of what I did there was listen to jazz and mountain bike. This is a great place for mountain bike. In that time, I also had a daughter. So my life no longer consists of this. It mostly consists of this, which is hanging out with my lovely daughter, who I get to see every day, even though I do not get to see her. Now, back to research. So approximate computing. What is approximate computing? So up here, just to explain this in this concept, what I've done here is put just a high-level abstraction of the way that we oftentimes think about our computing stack, like software down to hardware. So at the top, we have applications, compilers, operating system, hardware system. We've seen slides like this before. And something that was interesting, I was teaching my first class this past year, and at some point we talked about errors, just errors in our system, in our computing environment. And just by a show of hands, how many people think we have errors in our applications, right? We have errors, yeah, of course. Errors in applications, errors in libraries. Compiler and runtime systems, errors, yeah, we do. If you follow the research, there certainly will be some papers in PLDI about how we find and fix those bugs. Operating systems, yeah, operating system, we've all used Windows. And then hardware system, bugs, some, fewer, right? And this was the key. I was talking to my students, and they always just had this idea that if I had a program and I executed it on a piece of hardware, it was just going to execute that faithfully, and it should work, right? And frankly, that's how most people think. That's pretty much how I thought until my second or third year of graduate school, when I realized that is not the case. So, for example, something that you could do right now is you could go to the Intel website and actually pull the errata sheet for one of the processors. So this is for the latest 6th generation Intel processors, and there are about 107 current issues, and these issues range in severity. So, for example, one of these issues is that the performance monitoring events, when you're actually monitoring the CPU and you want performance counters, may actually be incorrect, right? That doesn't seem so bad. Now, at the bottom here, however, this doesn't seem so great. Right? Processor may hang or cause unpredictable behavior. Now, what does that mean? So hanging, that's bad. You know what that means. But unpredictable system behavior means that your computer may occasionally just return incorrect results and not tell you anything and just keep on running. And in practice, these do actually show up. Right? So recently, we saw this pop up with these 6th generation CPUs, actually, where these hang crashes were happening when you were running these particular stress test applications. So Prime 95, if you run that, if you're overclocker, for example, might have run this and you would have seen standard non-overclocked CPUs taken straight out of the package crash in your machine, cause your machine to hang. But also in this supercomputing environment, there's a place where we see this as well, where we have these computers that have hundreds of thousands of cores. And in that environment, when you're aggregating over all of these different CPUs and architectures, well, not necessarily architectures, but platforms, what you start to see is inconsistency. So for example, with one of these supercomputers, it was actually the case that you're seeing undetected errors at least once a day in memory, in your memory subsystem. And this is, of course, potentially going to cause issues with your program. So what do? Well, there's a little bit of a distinction to think about here, in that some of these errors are deterministic errors and whole set of things that you need to think about how you get rid of deterministic errors in the systems, but some of them are non-deterministic, and they come from a variety of events, a variety of places. So they could be logic errors, where again, the complex workloads come together, and the designer of that system and that circuit didn't think about something, and it's going to hit a corner case and it's going to crash. But there are also, these chips are actually physically manufactured. And the smaller they get, the smaller transistors get. Actually, the more susceptible they are to variation in this physical process, as well as environmental variation. So these sorts of things can actually cause these systems to non-deterministically produce different results and transiently fail. So now what do? Well, there are a couple options. One is you can replicate. This is a standard technique. So if I have some snippet of code for the sampleless edition, what I can do is replicate that, run a new, completely different copy, and then compare the results. Right? So that's one solution. What's the downside? The downside here is that, one, overhead. I have to run a whole nother version of my program. That's going to be overhead. As well as if this computation makes any changes to the state, I now need to checkpoint the entire state of the computation. That's not so great. So something that some people do is that for some applications, for example, Newton's method, where we're going to take some function and find a zero of that function, what we can actually do is very quickly check to see if we're actually going to get, or we got a correct result. So for example, here, when I have Newton's method, I pass it a guess and some function, I'm looking for a zero, I get some x back. What I can do is just check to see if that x is close to zero or not, right? And if it's not, then I'll go ahead and re-execute this computation and try it out again. So this solves some of our performance concerns because now we just have to deal with a few simple instructions for checking if we get a correct result, but we still have this whole checkpointing issue where perhaps if some gnarly side effect and computation is going on there, we need to potentially checkpoint a large part of the state. So what if instead we just let errors happen and just keep executing? Right? This would solve that problem. Right? Our program's going to be faster. It's going to consume less energy. And we don't need to worry about checkpointing all the state. Right? But what's the concern? Well, maybe you'll get a wrong result. But, approximate computing, what it's all about is actually telling you that it's not just a wrong result, it's a different result. Right? And the real question is, just how different is that result? Right? And there are a wide variety of the ways this result can be different. So it could produce an inaccurate result. Maybe most of the time it actually produces the correct result. But occasionally it does not. Right? But maybe that is too low. It's not reliable enough. Or it may produce some invalid result, something that's completely garbage. Or it may crash, do something nefarious. Perhaps that's what we're really concerned about. So approximate computing is how do we go about enabling applications to execute through errors and still produce sensible results. Right? Of course, this is PLMW, so the answer is we build a programming language, a programming methodology to support specifying the properties that we care about our programs and making sure that under these modes of operations, our programs can still execute. Now, there's a little bit more than that, right? So if we go back to our stack, right, okay, we've got hardware errors. But we've also admitted that there are errors in other parts of our execution stack. And in fact, this presents an opportunity, right? The observation here is that somehow our applications are mostly functional, even in the presence of all these other errors. So can we actually exploit this for additional performance? So for example, this is a transformation that done in my group where we actually take loops in your application and transform them so that they execute for fewer iterations. Right? Clearly what's going to happen here is this loop is going to execute more quickly and consume less power. Right? Fantastic transformation. And in fact, this actually tends to work. Right? So what does happen in practice is, so what I have here is a single video that's gone through two versions of the X264 video encoder. The version on the left, standard X264 video encoder. The version on the right has gone through a version where we've applied one of these transformations, where we've selectively found loops to actually drop iterations from. And although there are some minor differences, it's actually really funny. Sometimes this video gets really corrupted just because PowerPoint is terrible. But there are minor differences in the one that we're seeing here. And the real difference, though, is that encoding this video on the right is two times faster than the video on the left. So inspired by this, I, along with many other people in our community, have come up with a variety of ways of actually exploiting this observation that applications can be naturally resilient to errors to propose transformations. So we see code preparation, but we also have things like function substitution, where take a component in your application and we're going to replace it with a new component that approximates its behavior. So one thing that's done here is replace it with a neural network, something that's been trained to learn the behavior of that component. Other things we've seen are things like relaxed synchronization, where we actually go in and take a parallel application that has locks in it and remove some of those locks, enabling parallelism. introducing data races and changing behavior of the program. And then finally, approximate hardware. So we talked about hardware at the beginning, where hardware is inherently unreliable, but people are actually thinking of ways to actually build, frankly, less reliable hardware, hardware that exploits these properties to actually get better performance and energy. And part of the reason why any of this stuff works in practice, right? You kind of have in your mind this grand vision of applying this for all sorts of programs, and this is going to work fantastically. That is unfortunately not the case. But typically where this does work is in uncertain computation, like machine learning, image processing, search, where there's this large trade-off between the quality of the results that a computation produces as a function of the time or resources that it takes to compute that result. And this is fundamentally a natural aspect of this case. So now going back to these applications, or thinking about this, or actually just for a step. So this trade-off, these applications, this is why this works. And it actually gives us this opportunity just from the beginning. So now back to our question, original question. So we're getting different results. How can we possibly be ensured that these applications can still be reasonable? Well, let me give you a simple example to make this more complete. So the example I have here is that of image scaling, where I have an image on the left, I'm going to scale it up to produce this image on the right. And a common way of implementing this is a kernel called interpolation, and this is just one of many different ways. And the way this works is that for any pixel in my scaled up image, map this back to a neighborhood of pixels in my original image, and then take some function of that neighborhood and set that to be the result of my pixel in the scaled image. And just a very simple implementation of this is as follows, where I have for some pixel x and y that I'm going to compute my scaled up image. I'm going to do that map step that I talked about. I'm then going to find those neighbors in the original image. Then I'm going to sum them up. And then I'm going to average them together, right? Very straightforward. You don't really need to think about this code too hard. Now, for this methodology, if we want to actually solve these problems, the way that we're going to think about doing this is that first we have this application, which is one point in this trade-off, right? And then we're going to define a safe execution envelope, places in the space where it can comfortably and acceptably execute for my particular domain. Then we're going to relax its semantics. So the relaxation itself is going to introduce new behaviors, which are behaviors that were not in the program before. So behaviors where we return different results. And finally, we're going to verify that these new behaviors still actually fit inside the safe execution envelope. And therefore, this is an acceptable program, even though it may do things I didn't necessarily anticipate. Right? So for a safe execution envelope, we can look at this. And one is this is actually using, so this neighborhood is this specification of indices into the source image. And one problem here is that we want these array accesses down here, or accessing source, to actually be in bounds. So this is one particular safety property that we care about, and there are a variety of other different safety properties that we may care about as well. But we can specify these safety properties with standard assertions that you see in your program. Now, the second part is we want to relax the semantics. So here in our work, something that we've introduced is this relax statement, which will non-deterministically modify some subset of variables in your program state subject to a constraint. So here we're going to change the value of n such that its new value is less than or equal to its old value. And what that means is that that's going to truncate the execution of this loop. Therefore, implementing basically a sampling. We're going to sample our neighborhood when we compute this average, which now makes sense. Like, why does loop proliferation make sense? Oftentimes because it looks like injected sampling into an application. So now, this relax statement is actually more general as well. We can represent other types of sampling, structuring the way that we modify this loop. We can also represent distortions, just arbitrarily corrupt some value. And this can very well capture what we might see from approximate hardware or unreliable hardware, where suddenly some value is going to be corrupted. We can also put a bound next to it as well. And these can be provided by a developer who perhaps is anticipating running their application on hardware that they know to have issues, or in the case of loop proliferation, we can build a compiler that can insert these ourselves. So now we have this original program. And when we add this relax statement, now what you can see is now we've expanded its behaviors. Like any choice of this n is now a new execution in this space, and it gives us a whole family of programs. As long as we verify this family, we can be ensured that any specific instance of this family will also be safe according to our definition. So again, safety, array access. This is what we care about. And if we want to verify this, verify this new program full outright, it'd actually be a little complicated. It wouldn't be so fun. We'd have to actually go and look back and get neighbors, make sure that the indices that we're getting back are sensible, and the relation to the mapping step that we had before. What that means, if we want to verify this, this local change that we're making requires global reasoning through the program. And that's not so much fun. Now, the observation instead, however, is that this local change can actually be pretty effectively characterized for this assertion in the sense that we don't actually modify the length of sorts, and we don't modify the contents of y's, even though we are changing the number of iterations of this loop, right? Those things do not change. And therefore, we really shouldn't we should not interfere with the validity of this assertion. And in fact, in our work, what we've done is we actually defined a new verification concept, including a program logic and framework for actually doing this sort of verification, where you assume that your assertions in your original program are actually valid. You assume that this array access is valid. And then we verify relations between the original program and this change, this approximate, this relaxed program. So for example, the length of source and the contents of y are the same, and we can specify this with a relational program logic. This is different from a standard program logic where you think about a single execution of a program. This is actually going to refer to multiple executions of the same program. And here we can refer to variables, for example, source in the relaxed program by source in the brackets r, and source in the original program by source in the brackets o. And now we can write assertions, and actually relationships between the two programs. And then finally, we're going to use these relations to actually verify that our relaxed program still satisfies this assertion, or should still satisfy this assertion. Specifically, if our original program satisfies all its assertions, then our relaxed program satisfies all its assertions. Right? And this is actually really important. Really important, particularly because if I actually do find a bug in my application, which of course we've admitted that actually happened, we can be sure that that bug actually exists in the original program and was not introduced by bug. So now, just to wrap up, we can go back. We got safety properties out of it. We had some technical results today. And there are these other considerations that we have as well. So we're concerned about the accuracy of these results as well as the reliability of these results. And with safety properties, we specify these as with standard assertions. And for these, for accuracy, we can actually specify this with this new relational program logic that we now have. We can actually specify this assertion and verify it using our logic. Now with reliability, this is actually a little bit different. Right, this is a probabilistic judgment. This is not a standard judgment where we're concerned about all executions of the program. Now, how do we do that? Well, what we've actually done is, in separate work, sit down and actually specify a probabilistic relational program logic that allows us to reason about the probability that these relationships are true between the original and relaxed program. And this is important because we can take something like the reliability and actually tune our reliability to allow this application to produce a correct result or a good enough result. As you can see, as we make the computation more reliable, specifically interpolation, more reliable, then each pixel will actually has a higher probability of being correct. And as long as we get enough pixels to be correct, then the image overall looks fairly acceptable. And there's some point at which that happens. It does not need to be fully reliable. So again, this has come up through a variety of different work that we've done over the years and still continue to do. And the conclusion here is that there are many opportunities to approximate programs and essentially fundamentally break the way that we think about compilation. Compilers are supposed to preserve the semantics of the program, and now we're changing that. Changing that with some benefit, right? Either allowing us to deal with unreliable hardware or actually get better performance. And the real takeaway here, though, is that for many of these, the reason why this works is that for many of these uncertain computations is that there is this trade-off. And going forward, we're going to see a much larger role of these applications in our everyday computational fabric. And it's important that we think about the probabilistic and relational judgments that go into reasoning about these programs. So that's it. Happy to take questions. So you mean I'd want to separate. The relaxed program has a different set of properties than the original program. So in our framework, you could actually add that using basic assertions that actually only apply to the relaxed program if you wanted to. Yeah, certainly possible. But then you get back into the standard verification process, right? A lot of this is what you're interested in, is that you have correctness criteria about your original program. You just want to make sure that your relaxed program still satisfies them, right? As long as your original program did the right thing, your relaxed one should as well. Yep. Yep. So wait, so let me try to just, yeah. Yep, yep, yep. Mm-hmm. Mm-hmm. So if precision really, really matters. Oh, I see. So make sure I summarize this accurately. Um, so one basic concern is how do we preserve, how do we reason, so reasoning about precision is already hard enough in existing applications, right? That's one part of it. So how can we hope to do it here as well? So frankly, actually, part of the reason, part of my research agenda through graduate school was actually motivating additional opportunities for verification. So if here in these cases, you could actually get improved performance by annotating your original application and doing verification there, and doing a small amount of verification for this relaxed program, then that can actually motivate people to actually do more verification about their original program. Right now, the entire motivation for this as well is based on this reality, right? People are already concerned about their programs. Can their programs do the right thing? Why are we going to make it more complicated? And frankly, when we first started doing this work, we had lots of empirical results. And those results were constantly rejected from the conferences for this exact question. And this is why we developed this work, is that it was actually possible. Some additional work to actually put bounds on the behavior of the program. Yep. 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 Exactly. Yep. Mm-hmm. Yep. Mm-hmm. Yes. Yep. Yes. I entirely agree with that, right? Often, I mean, yeah, I mean, and oftentimes for these computations, right, the receiver of the computation is human, and we are very good at dealing with error, at least in comparison to a program or a computer. Now, I think what is important, what is part of the discovery here is how do you overall architect these systems such that you have a core component that is hard and logically constrained with exact guarantees, using the full weight of verification techniques that we have to enforce that, and then enforcing a separation between this uncertain world. Right? I think you're very right. I think it's still very open, broadly speaking, how we build these cyber physical systems. And this is why you see so much work